This session is going to be updates from previous workshop presenters. So our group Climate Change AI has held workshops at previous conferences, including ICML, NeurIPS, and AMLD. For those who don't know, who are tuning in just for today, this workshop is in conjunction with the iClear Machine Learning Conference. And we're going to do this session a little bit differently than the other sessions today. It's going to be hopefully a little more participatory and allows some time for kind of small group discussions. So what we'll do is we'll have each of our presenters give a short talk on both their previous work and how it's progressed since then. And we will kind of presenters, I'm going to keep you to exactly 5 minutes or as close as I can so that we can have half an hour for the second part. So in the second part of this session, we will actually break into breakout rooms to have smaller groups of discussions with each of the presenters. I will initially assign these randomly, but if you want to be put with a different presenter than the one you end up with because you have specific questions for someone, you can come back into the main room and make that request. So let's see how that works. It'll be a little bit different from the previous. So our first presenter in this block is going to be Chris Heinrich, who's going to talk about roof age determination for the automated site selection of rooftop solar, which was work presented at AMLD. Chris, feel free to unmute yourself, share your screen.
Yeah, thank you, Priya, and thanks to all the organizers for putting this awesome workshop together. Can you all see my screen now?
Yes.
Yep, okay. So I am going to talk about roof age determination, and in particular, how we determine roof age using deep learning, and why that's an important thing to do for automated site selection of rooftop solar, and therefore for climate change. My name is Chris Heinrich, and I'm based in Los Angeles. So first of all, I'd like to give a shout out to my collaborators, Michael Laskin, who's a postdoc at UC Berkeley, Seamus Glinskis, a recent graduate from the University of Chicago, and Everett von Neuenberg, an assistant professor at the Niels Bohr Institute. The outline for my talk, which I'll try to squeeze into 5 minutes, is I'll first spend most of the talk trying to convince you that roof age is an important quantity for solar developers. I'll explain briefly how we were able to determine that using machine learning, and then what we're working on next. So first of all, why rooftop solar? It has the potential to displace a large amount of CO2. It's a top 3 source of renewable energy, and it's one of the top 10 interventions for tackling climate change. And so we'd like more solar, and how do we get more solar? We do that by making it cheaper. Here's a plot that shows, the yellow line shows the cost of solar over time going down, and a clear trend that shows as solar price goes down, we get more solar deployed each year. So one way to get more renewable energy, and that's one of the messages from this talk, is to find interventions and ways to make deploying renewable energies easier and cheaper. And the costs of the hard costs, like the material costs of solar, have come down so much that soft costs like labor and customer acquisition costs really dominate the cost equation. In particular, customer acquisition costs, and this means solar developers spending budget on sales and marketing and outreach, finding the right buildings to sell renewables to, accounts for about 20% of the total cost of installing solar. So it's really, it's only maybe half as much as the materials cost, which is kind of hard to believe. And it's a prime target for using machine learning to try to bring this down. And there's a lot of things that impact customer acquisition costs. The focus of this talk is building roof age. And that's because solar developers end up wasting a lot of money on buildings that have the wrong roof. Buildings are, and this is because solar systems last for about 25 years, and roofs, at least for large commercial and industrial buildings, last about 30 years. So the best age roofs are either new roofs, which will last for the lifetime of the array, or very old roofs, in which case you can replace the roof and install solar at the same time. A lot of roofs fall somewhere in the middle, and solar developers don't generally find this out until after they've wasted a lot of money marketing and trying to do outreach to these building owners. And that's why a data-driven approach that helps you determine the roof age upfront will allow building owners to or solar developers to save a lot of money. And it's important that we do this in an automated way that saves costs. And we estimated that if all building owners, or if all solar developers knew this ahead of time, that it could displace about 760 megatons of CO2 just by knowing this information. So in terms of determining roof age, we need a cheap, scalable method. And like a lot of other presenters in this session, this means one way to do this is try to leverage aerial imagery. And so from a single aerial image, it's very hard to tell how old a roof is. But if you look at multiple images over multiple years, what you notice is that at some point the roof looks very different from one year to the next. And this was when the roof was replaced. And because the roof was replaced in about 2016, for this roof, that means this roof is about 4 years old. So that's sort of the key insight that allowed us to develop a machine learning solution to approach this problem. And the rest is sort of history. You know, we built up a data set by intersecting public building permit data to get ground truth roof ages in Los Angeles and historical aerial imagery to get these sequences of images. Running low on time, but we have more details in the paper, which I'll link to at the end of the talk. We developed a machine learning algorithm to try to detect these re-roof transition points. And we would, for a sequence of images, predict for every consecutive image whether or not the roof had been replaced during that time. And that this would lead us to a prediction about the roof age that, at least on our test data set, was more than accurate enough for solar developers for this particular application. We had an error of about 0.68 years. So with this, I will skip to the end of my talk. Briefly, what we're working on in progress is bringing this solution to market, which requires getting more data and trying to do a better job. There's more details in this paper, or if you're interested, you can reach out to me. Thank you.
Wonderful. Thanks, Chris. And also thank you for self-moderating on the time. So the next presenter is Neel Guha. So Neel, go ahead. And Neel will be presenting on his previous work, Machine Learning for AC Optimal Power Flow from ICML 2019. Neel, we can see your screen, but if you're talking, you're muted, I think.
Can you hear me now?
Yes.
Awesome. Sorry, I'm struggling with Zoom a lot. All right, so yeah, like Priya mentioned, I'm going to be talking a little bit about some work we presented at ICML 2019 on machine learning for AC optimal power flow, and this is joint work with Jason Wang, Matt Wytock, and Arun Mushimdar. So maybe starting from the top, why do we care about grid optimization in the context of global climate change? Well, as I'm sure as you're all aware, increasing our reliance on renewable sources of energy is a really important step towards fighting global climate change. And it turns out that one of the main inhibitors for improving the amount of solar energy or wind energy we use in our grid is the difficulty in actually balancing the grid and managing power with these renewable sources, which can tend to be a little bit intermittent and introduce all sorts of computational challenges. Now, within the actual problem of managing the grid, a really important and a really challenging subproblem is known as AC optimal power flow. And there are like 60 years of literature on this problem, but for the purpose of this talk, you can think of AC optimal power flow as essentially a really hard constrained optimization problem. In this problem, our objective is to minimize the operating costs of generators on the grid, where the cost of a generator is a function of the amount of power it's outputting. And there are really three types of constraints. The first type of constraint is that the demand for power matches the supply for power, so everyone who wants power is getting power. The second type of constraint, or what we refer to as physics-based constraints, essentially that the laws of physics are being satisfied across the grid, and this concretely translates into the power flow equations. And the final type of constraint is what we call mechanical or safety constraints, that different components of the grid are operating within safe limits. So this could be minimum maximum voltages, minimum maximum branch flow, or sort of limits on the amount of power a particular generator can produce. And on this slide, you have this problem in English on the left and in math on the right. Now, it turns out that AC OPF is really, really hard. It's non-convex and NP hard. and that in the amount of time grid operators have, they're not actually able to solve ACOPF. So instead, they solve an imperfect linearized version of this problem known as DCOPF. Unfortunately, this has a lot of challenges. It can create great instability. FERC estimates that we're losing billions of dollars by solving this version of the problem instead of the original ACOPF problem, which sort of led to the observation or the intuition of our work, which is that maybe we can actually apply machine learning to somehow help in this pipeline. And this was based off two observations. The first was that load distributions and corresponding optimal configurations have patterns. If the load today is very similar to the load tomorrow, then I naturally expect that the optimal solution today is very similar to the optimal solution tomorrow. And the second is that machine learning is really, really fast at inference, and that what machine learning allows us to do is essentially take a lot of the work and move it offline where we are free from these time constraints. And thus we can perform inference in milliseconds. And that could potentially give grid operators a very valuable tool for solving this problem. So what does this look like from a pipeline perspective? You can imagine grid operators accumulating historical data and using an AC optimal power flow solver to generate solutions offline. Because this is happening offline, they're not burdened by time constraints. Using this data, where you can think of your X as the input to the problem and your Y as the solution to your problem, you can train a model. And then at operation time, you would run your model over the current grid configuration you see to generate a solution and take an action on how to manage the grid based on that solution. And so in our work, we tried to explore, well, does this even work? Can we even try it? And we looked at two variations. Can we, one, learn a model to in a sort of end-to-end manner to just predict what the optimal solution could be? And then the second case, can we actually predict something about which constraints are active? And we found that when our model's outputs satisfy the constraints, the average cost of the model's output doesn't vary a lot from the optimal solution, and that the models can actually be quite good at predicting which constraints are active. So of course, moving forward, what are the future directions we see here? There's been a lot of new and really interesting work building off of this on different ways of incorporating constraints, different ways of leveraging network structure, including graph neural networks. But by and large, one of the things we need to think about as a community as we explore this problem more deeply is how can we develop a set of coherent benchmarks with which to evaluate these different methods. This is a very complex problem where success has many different definitions in terms of balancing constraints and meeting, minimizing an objective. And so this is really a call towards the community to have a conversation about how we develop these data sets. I think with that, I'm at 4 minutes and 59 seconds. So I'm going to wrap up, but thank you so much for taking the time.
Thank you, Neel. That was great. So let's see, our next presenter is Kalai Ramea, who is going to be presenting work on unsupervised temporal clustering to monitor the performance of alternative fueling infrastructure. And this is work from ICML 2019. Kalai, thanks for already sharing your slides. You're good to go.
Yeah, can you hear me?
Yes.
Okay, I'll get started. Hi, everyone. My name is Kalai Ramea. I'm a research scientist at Baasch working on machine learning and AI applications for climate and energy systems. Today, I'll be giving a short presentation on a project I did last year on monitoring performance of alternative fueling stations using machine learning. And here I'm going to demonstrate it for hydrogen infrastructure, but you can think about these approaches that can be generically applied to natural gas or biofuels and so on. Yeah. So whenever people think of zero emission vehicles, right? I mean, battery electric cars are the first ones to be considered as a solution. And though it's true to a large extent, and they have been contributing in decarbonizing transportation sector, it is beyond certain threshold, it's more complex to do that. So we need to give consumers technological diversity to address that. For instance, electric cars have limitations on long charging time or range anxiety, and there are some long-term concerns on like lithium mining and scaling up the grid. So we need to consider alternative fuels such as hydrogen and natural gas, and it has been proven that larger size transportation modes such as buses, ships, and heavy-duty trucks do better with such fuels. So that is the reason for diving into this project. So I'm going to be talking about fuel cell electric cars and hydrogen stations here. If you're not familiar with it, these are another kind of electric cars that runs on fuel cell instead of batteries. And they are being sold in California since 2015. They use fuel cells and hydrogen to convert to electricity. And there are dedicated hydrogen fueling stations in California. And it takes about 3 to 5 minutes to refill and has pretty good range. And as you can imagine, availability of reliable fuel is one of the biggest barriers for widespread adoption of these vehicles. And here's a picture of what a hydrogen station looks like and how it's being fueled into the car. It's very similar to gasoline. And there are about 42 hydrogen stations in California as of today. And I actually drive one of these, so that is the reason how this project idea came about. I personally wanted to know which stations are more reliable and which ones have issues so that I can avoid them. But there was no quantitative information on station reliability, and that's how I started collecting data and I did a research project on that. So as the first step, I collected the real-time hourly fuel availability data for all the stations in California. There's a website called Fuel Cell Partnership. So I did that for 3 months. And simultaneously, I also did a qualitative survey from about 100 fuel cell drivers in California, mainly to understand their preferences and complaints about the stations that they refuel. Now that we have both quantitative and qualitative data, I wanted to see if the time series data that we collected has any specific signature or characteristics. So I did a temporal clustering algorithm for that. I'm going to skip the technical details for now. I'm going to reserve it for the breakout sessions, but there is a paper published on it if you don't get to attend that. So we can go through that. So this is the output of the temporal clustering algorithm. As the right side shows, there are different types of temporal signatures of these stations. And qualitatively, we can sense that some are busy, some are more regular, and some are constant. This is where the survey that we did helped to categorize. So the users described these stations as different kinds of things. So we were able to map that to the cluster categories. They described that most of them as reliable and some overstressed, some are non-standard reporting, and so on. I also mapped the categories to the preferences of these stations. And not surprisingly, users preferred those stations that are reliable compared to the others that have issues. So this was the work I presented at ICML last year. And from then I extended this work to include the spatial component by incorporating neighborhood demand. So I did some analysis on willingness to drive of the drivers. And not going into too much details on the technical approach now. It's published in the journal below that's noted here. We can also discuss this in Q&A. Just know that this plots the utilization and demand for each station. And if the station lies in the green band indicated, which is called the satisfactory utilization range, then it's considered to be a preferable one. Now, how can this benefit policymakers? You can combine the approaches described earlier. So people can use this in a continuous monitoring fashion to identify problematic stations, plan for any disruption, and eventually to increase reliability among drivers. So to summarize, California has ambitious plans to expand hydrogen fueling infrastructure, about 200 stations by 2025. This not only requires proper planning, but also some proper monitoring approaches so we can increase reliability of these stations. Again, as I mentioned earlier, though this is demonstrated for hydrogen, it can be applied to any kind of alternative fuel, such as natural gas or biofuel. And these are the 2 publications that came out of this work. So feel free to go through them. And I'll take any questions in the Q&A session or through offline. Thank you so much.
Awesome. Thank you, Kalai. The next talk is from Ján Drgoňa about stripping off the implementation complexity of physics-based model predictive control for buildings via deep learning. And this was presented at NeurIPS 2019.
Hi, Priya. Thank you very
much. Hi,
much.
Ján. Of course.
For organizer for putting this amazing workshop. So I hope you can see my screen by now.
Yes.
Right? Okay. So I will give you an update on our recent work on using deep learning for cutting the cost of the physics-based model predictive control for buildings, which was done at the Pacific Northwest National Lab together with my colleagues Aaron Tour and Drgoňa. So why buildings? Because buildings generate almost 20% of the greenhouse gas emissions globally and consume a huge amount of energy. So one of the solutions which have been identified is to use optimal control to cut the emissions. So this comes with the promise of emission savings of almost 30%. However, the wide-scale solution of the optimal control in buildings is still like not happening. So what is the reason? So the reason is simple, because the advanced controls are just too costly for the current buildings. So in our previous work, we have demonstrated how the physics-based model predictive control can save up to 50% of the energy use. And subsequently, we showed how we can use deep learning to cut the implementation cost of these high-fidelity physics-based controllers using surrogate modeling and implement subsequent implementation in the building to cut the implementation costs. However, by using this approach, we are solving only half of the problem because we are saving the cost on the implementation part, but we still depend on expensive physics-based modeling. So as an update, we propose a solution of using physics-based deep model predictive control, which is based on the reformulation of the traditional model predictive control as a deep learning model, which you can now train end-to-end from data. So the idea is to take the structural equivalence of the traditional model predictive control, formulate deep learning model embedding those constraints satisfying the building physics, inequalities on your states and input actions directly into the architecture. So here, the building physics model is given as a constrained recurrent neural network, when this A transition model represents now the building heat transfer, for example, and the B represents the input dynamics model, which consists of your heating system or the influence of the disturbances. And now you can train the parameters of the building model such that it fits the data simultaneously with the policy which controls the building heating system. I'm going to skip the technical details. They can be found in our paper, which was published on arXiv recently. But I'm just going to give you like tutorial example on intuitive building model with single zone to demonstrate the capabilities of this kind of policies. So here we are able to train the system model together with the control policy from one week of data and generalize over consecutive weeks purely based on the input-output measurements of the building dynamics. So the objective here is to control the room temperature following the reference given in dashed blue, while satisfying inequality constraints in the dashed black, while still also satisfying the constraints on your control actions and being influenced by the disturbances, which can be like the ambient temperature or solar radiation or occupancy, internal heat gains. So the bottom line here is that we are able to train end-to-end system models which satisfy the physical constraints and generalize over a large period of time on previously unseen operational conditions. The dynamics is parameterized as unknown neural difference equations. The stability of the system model is satisfied with constraints on the eigenvalues of the system model, which can be represented as a heat losses or the dissipation of the system model. And inequality constraints are modeled with penalty methods embedded in the deep learning model. And we are currently working on extending this approach to larger, more complex nonlinear systems in energy domain, manufacturing, and material processing. And all code will be released soon after internal review on the PNNL GitHub webpage. And if you are interested in benchmarking the model predictive control based on white box model in MATLAB, you can also check my GitHub webpage. Thanks very much for your attention.
Thank you. That was 4 minutes and 59 seconds. That's pretty perfect. Good work. So thank you for your presentation. And next is Jacob Pettit. So Jacob's work was on increasing the performance of electric vehicles in ride-hailing services using deep reinforcement learning and was presented at NeurIPS 2019. So Jacob, are you able to unmute yourself and share your screen?
Okay, yeah, sorry, I had to figure out how to unmute myself. 1 second, yeah.
You're good. Yeah, we can hear you, so all good.
Okay, perfect. Okay, great. Okay, yeah, so hi everyone, thanks to Priya and the other organizers. So our work, as you said, was at NeurIPS last year using deep reinforcement learning to increase performance of electric vehicles. And yeah, so, you know, EVs are not used very commonly in things like Uber and Lyft in these ride-hailing services because of the limited range, long-range charge time, and long-range EVs are very expensive. There's limited charging infrastructure, so there's lots of scarcity to being able to get to even charging stations or to fast charging stations. There we go. Well, sorry. Okay. Yeah. So our approach was to build a simulated environment of the ride-hailing electric vehicle, and then train a policy using deep reinforcement learning in that environment to make decisions about, you know, when and where to charge the car. We wanted our policy to, you know, minimize the time spent charging and the amount of money that they spend on charging, and of course, act as efficiently as possible, while also making the driver as much money as possible and driving as many miles as it can. Briefly about reinforcement learning, you know, you have an agent takes in some state and some reward, and then takes an action, and then receives a new state and reward from the environment, and this continues in a loop until our episode of interaction with the environment concludes. And our observations in this case, we had to give the agent enough information to act how we want it to, and so it was given information about the current battery level of the car, the time of day. The time of day was given because cost of energy and waiting time to charging stations are correlated to time of day. Expected battery usage and expected charge cost were given, and these things are expected based on the next expected ride given, you know, the current state. So how long it's expected to take, and so on. And yeah, the travel time to the closest charger, the expected ride duration, and our current location on the grid are all given to our agent. So we went ahead and developed a very data-driven simulation of an electric vehicle driving for a TNC. We modeled things like the electric grid, the electric vehicle, our charging stations in terms of wait times and the rate of charge that flows from the station. And the ride-hailing company was modeled just as a sort of as a structure that gives the driver new rides to choose to go and take or not. Our wrapper, we're calling it, around the agent in the simulation handled interactions between the agent and the environment and gave reward signals to the agent. The agent, of course, takes in the states in the simulation and then the rewards and chooses actions that it believes will maximize its future reward. The reward function itself, right? So the agent gives a ride, the battery gets dropped off, and the agent gets rewarded for making money, which is good. If we choose to charge, the car battery is always filled to 100%, and the agent gets a penalty for paying for energy and for producing emissions by using electricity. When the agent tries to take a ride, but maybe we have only 10% battery or otherwise don't have enough to deliver that ride, then now we're like forced to charge the car, and then we also have a much higher penalty because we would have ended up stranded on the side of the road. Just as a quick visualization, right, we worked on, our environment was modeled off of Manhattan. So for example, you're at some starting point and a drop-off point is generated and you go there. And it's very, very simple. So for results, we used the off-the-shelf algorithm TRPO, and we got compared to, and so, oh, whoops, these thresholds are, if our battery is 10%, then take a ride. If it's at 25%, then take a ride. And if it's at 50%, or rather, if it's at 10% then charge, 25% charge, 50% charge. So the TRPO is beating these thresholds, and these thresholds were ideally considered to be a reasonable proxy for human behavior because, if my car is at a quarter tank, then I'm going to say to myself, oh, it's time to go get gas. Or if I'm, at empty, then, the E light comes on, and of course, it's time to go get gas. And so we're trying to capture a moderate spectrum of human behavior and compare against these thresholds. And so TRPO on average gets better reward, and the distribution is tighter, which is great. And we also, on average, spend less money on charging the car over the episode, which is also a good result. And just another way of looking at this, overtraining, our reward might start lower, but it quickly goes up over time and is on par or sometimes better than these other thresholds. And yeah, so that's another reward plot. That's everything I have. And we demonstrate the feasibility of using RL, and in the future, we're gonna expand our simulation and increase the quality of what we're working with. Now, yeah, thanks.
Awesome, thank you, Jacob. And then our last presentation before we go into breakout rooms is going to be Gaby Baasch. Gaby's work is on targeting buildings for energy retrofit using recurrent neural networks with multivariate time series, and was presented at NeurIPS 2019. So Gaby, could you share your screen?
Hi, can everyone see my screen?
Yes.
Okay. Hi, everyone. Thanks so much for having me here. I'm really excited to have the chance to speak with everyone. I'm a master's student at the University of Victoria in the Energy and Cities Lab. And today I'll be talking to you about targeting buildings for energy retrofit with supervised learning. So to start, I'll just tell you a bit about us so you understand our perspective. We are an interdisciplinary research team based in British Columbia, Canada. We're interested in buildings and cities, in particular climate mitigation. So we work very closely with government and industry to develop tools that can be used in practice. So a smart energy retrofit is the process by which you take an existing building and update it so that it uses less energy. Retrofit can come in many different types of forms, but two that I'll be focusing on today are heating system upgrades, for example, updating to a more efficient system like a heat pump, or building envelope upgrades. This can include improving the thermal insulation quality of the windows and walls. So some of you might know that buildings use approximately 30% of energy globally. For this reason, experts say that retrofits are actually required internationally for us to meet our emissions targets. This is where we think supervised machine learning can really help. Compared to traditional approaches, they're cost-effective, fast, and they're scalable. So they can really help us leverage our resources and perform retrofitting in a smart way. That said, these methods aren't widely used right now. There could be many reasons for this, some of which might include a lack of understanding from what we can learn about building sensor data, and a lack of data with interesting labels. So with that, I'll present the two case studies of this work. Each of these tries to overcome one of these aforementioned issues. So in each of the two case studies, we use a different data set. But for each case, we use a multivariate time series data set, where the input is the time series data with 2,000 time steps. In case one, our output is a Boolean that represents the presence of a heat pump, which again is an efficient type of heating system. In case two, we output a float, which represents the building R value. The R value quantifies the building insulation performance. So in case one, we use a real-world smart thermostat dataset provided by a company called Ecobee. And in case two, it's actually very difficult to find building data with R value. So we actually create our own data set using a synthetic simulation software called Energy Plus. And I should mention in both of these cases, we're looking at residential buildings. So for each of the two case studies, we use the same neural network architecture. This is just a simple recurrent neural network with GRU layers. So in the heat pump classification case, we achieve an accuracy of 0.87 on the test set. This is a good result and it's very promising. It confirms our hypothesis that we can use building sensor data to predict mechanical heating systems in a building. In the second case, we predict the insulation performance, which is the R value. We can see from the figure that there's a very close relationship between the predicted and the actual values, and we achieve an RMSE score of 0.089. Again, this is very promising and confirms the hypothesis about what we can learn from sensor data in buildings. Additionally, the contribution of the synthetic data set used for training is a significant contribution of this work. So with that, I'll talk a bit about the limitations on our ongoing work. So this is a very promising result, but this is more of a proof of concept than it is a full-scale study. So of course, the first thing that we're going to do is work on extending that. We're working on scaling up this study. So we're generalizing the data sets further and increasing the data set size. Generalization can include things such as moving to more different types of climates. Once we do this with the synthetic data set, we're going to publish this work so that other researchers can use it to develop their own algorithms. We'll be publishing this alongside things like the R value and many other types of building metadata as well. We're currently working to extend this work to include more network architectures besides just the RNN. For example, we've implemented a one-dimensional convolutional neural network, and we're testing that out and comparing the two right now. Besides just comparing the machine learning approaches to each other, we're working on comparing machine learning approaches to more traditional methods for building performance assessment. We want to make sure that this really is the best approach for this type of problem. Finally, we're working on understanding how any model that's trained on synthetic data can transfer to real world data, because this is going to be essential if we want to use these models in practice. This is all part of a larger ongoing initiative that our lab is working on called the Rebuild Initiative. This is where we're working with government and industry partners to put these tools into practice. If you're interested, take a look at our website. And thanks so much. I'm excited to talk to all of you.